Dear ladies and gentlemen, the present contribution deals with the application of a non-local Gerson-Twergaard-Needleman model. The main focus is on the question how the model parameters can be calibrated. My name is Seupel. I am researcher at the Technical University of Freiberg, and I'll guide you through the presentation also on behalf of the co-authors Kuna and Fütter. In order to assess the integrity of structures in the presence of macroscopic cracks, the concepts of fracture mechanics can be applied. A numerical analysis enables to determine the crack tip loading, whereas the material resistance, for example in terms of a critical J value, is obtained from proper fracture mechanics testing. In case of ductile failure, the physical fracture mechanism is described as nucleation growth and coalescence of microvoids. This information isn't necessarily needed for the so-called global approach to fracture. The obvious limitation is the necessary existence of cracks. Their locations, sizes and shapes are often unknown, especially during design and safety analysis of new components. To overcome the limitations of the global approach, damage mechanics models have been developed as promising tools. Within the framework of the so-called local approach, the micromechanically motivated Gerson model seems to be of high interest for the description of ductile damage, besides others. A drawback of damage mechanics models is the well-known mesh dependency, which can be handled by gradient enhancement, non-local averaging, and so on. These enhanced damage models can overcome the limitations of fracture mechanics, but there are still some barriers which can hinder their industrial application. A severe problem is the lack of unique and reliable procedures which can be used to calibrate the constitutive parameters. Furthermore, non-local damage models are often not available in commercial finite element programs. User-defined implementations are required, which can be a huge barrier for practical working engineers. Within the present contribution, some of these aspects are discussed for a gradient-enhanced GTN model. An efficient implementation strategy using commercial finite element programs is proposed. The main focus is on the development of a reasonable parameter calibration strategy, which is finally applied to model the failure behavior of a pressure vessel steel. Let's start with some comments on the efficient implementation strategy. Firstly, the used GTN model should be briefly summarized. Detailed information can be found in the cited references. The GTN yield function is influenced by the void volume fraction. The yield surface shrinks towards the zero stress state, which yields the softening effect. Q1 and Q2 are the additional parameters introduced by Twergaard and Needleman. The porosity evolution is driven by the non-local counterpart of the volumetric plastic strain rate, highlighted by a bar. Therewith, the mesh dependency during softening is circumvented. Nucleation of voids is not considered in what follows. The mechanism of void coalescence is described by introducing the effective porosity F star. When the critical porosity Fc is exceeded, an accelerated void growth is defined, which is controlled by the slope k. The evolution of the non-local volumetric plastic strain is modeled by the implicit gradient enhancement proposed by Perlings. A field equation of Helmholtz type has to be solved, which contains the so-called internal length as additional parameter. The parameters to be calibrated are summarized here. For finite element implementation, the analogy between the Helmholtz type equation of the gradient enhancement and the steady-state heat equation can be exploited. Therewith, the coding of user-defined elements is circumvented. Instead, default thermomechanically coupled simulation tools of finite element programs can be utilized. Just a user-defined material routine for thermomechanical coupling needs to be defined. With the non-local implementation at hand, rather robust crack growth simulations are possible, as illustrated here, which are needed to investigate strategies for parameter calibration, as we will see within the following slides. A general roadmap has already been proposed by Fütter for the specific non-local GTN model. 3 steps are considered. From the microstructure, the initial porosity F0 can be extracted. The same is maybe possible for the void volume fraction due to nucleation, but that isn't considered here. A smooth tensile test is primarily used to find an appropriate strain hardening law. For different types of hardening, cell model calculations have been used in many previous studies to fit Q parameters. The set Q1 1.5 and Q2 1 seems to be an established choice for steels with moderate hardening, which is also utilized in our study. In order to determine the model parameters related to damage and fracture, experiments and simulations of fracture mechanics tests are needed, especially the crack growth resistance curves. The question can be asked whether results obtained from uncracked specimens like notch tensile tests can be used instead. Therefore, a sensitivity study is performed for a 4-point SANB scenario as fracture mechanics test and a round notch tensile test as uncracked specimen. For the elastic plastic behavior, properties of a specific pressure vessel steel are assumed, which exhibits a moderate strain hardening and a pronounced diffuse necking during tensile testing. Let's take a look at the results of the parameter study concerning the notch tensile test. Variations of the ratio Fc/F0, of the internal length, and the slope within the coalescence regime K are considered. The impact on the force versus cross-section reduction curve is investigated, which is the typical available output of notch tensile tests. At a glance, the ratio Fc/F0, the internal length, and the slope K have a similar effect, a shift of the failure point. All three parameters become only effective during the necking stage. A slight influence of Fc and K on the slope of the softening branch is visible, but it becomes clear that no unique choice of the parameters is possible, and therefore the notch tensile test alone isn't suited for identification purposes. On the other hand, for the fracture mechanics SANB test, the ratio Fc/F0 strongly affects the tearing modulus of the simulated R-curve. This finding for the GTN model is also known from previously performed systematic small-scale yielding simulations utilizing a boundary layer model. It is remarkable that the ratio Fc/F0 is important. For the SANB test, slightly changes of the initial porosity, but same ratios Fc/F0 yield comparable R-curves. Besides the strong effect of Fc on the slope of the R-curve, the fracture initiation toughness is directly influenced by the internal length. This fact is already given by dimensional reasons. Unfortunately, the slope of accelerated void growth, K, also shifts the fracture initiation toughness. At this point, further assumptions are needed. We propose to fix K right from the beginning, so that the ratio Fc/F0 and the internal length can be uniquely defined. It should be mentioned that appropriate sets of these parameters may be found for different choices of the initial porosity and the slope parameter K, which will be discussed later. The final strategy for parameter calibration of the non-local GTN model, which is now applied to the specific pressure vessel steel, reads as follows. A value for the initial void volume fraction can be estimated, for example with the help of the famous Franklin formula. We assumed a high, let's say upper bound value of 1% as initial porosity. Again, no void nucleation is taken into account. With the help of smooth tensile tests, the strain hardening behavior is investigated. In order to match the necking behavior of the considered steel, force versus elongation and cross-section reduction curves of experiments and full finite element simulations of the tensile tests have been used. Different hardening laws have been tested. The best result has been obtained by a combined linear exponential formulation. A 4-point SANB test is used to characterize the R-curve. After fixing K, the ratio Fc/F0 and the internal length are manually varied to fit tearing modulus and fracture initiation toughness. In this final section, the calibration results and the predictive power of the model are discussed. As earlier mentioned, different initial sets of initial porosity and K value may yield comparable calibration results. In order to test this hypothesis, the shown three parameter sets are considered. Indeed, nearly coincident results in terms of the R-curve are obtained. A good agreement with the fit function constructed from experiments exists from the 0.2 mm shift of the blunting line until a crack extension of 1.2 mm. For the three calibrated parameter sets, Simulations of differently notched round tensile tests have been conducted. The following force versus cross-section reduction curves show all a gradual descent after reaching a force maximum. This behavior is due to diffuse necking. Please note that the model is able to show this behavior because of the properly chosen strain hardening law. The damage influences only the onset of fast softening. Simulation results are denoted by solid lines, experimental results by dashed lines respectively. For all three parameter sets, a reasonable prediction of the failure behavior of all considered specimen types, smooth and notch round tensile tests can be concluded. Although the high initial porosity of about 1% is assumed, no severe deviations of the force versus diameter reduction curves are visible before the final failure sets in. Additionally, results of small punch tests are available for validation. The contour plot and the picture illustrate that the location of the final fracture is correctly predicted. The force versus punch displacement curves are in a good agreement with the experimental data until the force maximum. Again, the strain hardening law is responsible. The GTN simulations of the different parameter sets yield comparable results. Their predictions are closer to the experimental curves than a pure plasticity simulation, but they overshoot the upper bound from experiments. It should be mentioned that the lowest maximum of stress triaxiality in the fracture process zone of all considered tests has been found for the small punch test, approximately 2/3. Even the smooth tensile test shows a higher triaxiality during necking. Maybe the limits of the GTN model are nearly reached in the case of the small punch test. Let me sum up the presentation. We started with the aim to suggest a feasible calibration strategy for a non-local, purely void growth-based GTN model. As database, a set of two tests is incorporated, a smooth tensile test and a fracture mechanics test that provides the crack growth resistance curve for the considered material. These are experiments which are typically accessible also for practical working engineers. With help of the tensile test, mainly the strain hardening law is identified. The necking stage should be taken into account to find an appropriate approach. The study shows that not all three parameters of the GTN model can be uniquely determined. We propose to prescribe the initial porosity and the slope of the accelerated void growth. Then, the comparison of simulated and experimental arc curves provides the most important information. Tearing modulus and fracture initiation toughness are determined by the void volume fraction at coalescence and the internal length respectively. From the application, the following conclusions can be drawn. In general, a calibration seems to be possible for different but slightly varying sets of starting values for K and F0. A direct consequence of the proposed calibration strategy is the interpretation of the internal length and the void volume fraction at coalescence as fit parameters instead of fixed microstructural ones. There are further specific results for the considered pressure vessel steel. Firstly, a high initial porosity of 1%, which is uncommon for modern steels, seems to be suitable. The introduction of void nucleation isn't necessary, which is in line with recent literature findings. Please note that in the specific applications, moderate to high stress triaxialities and mode 1 crack growth are dominant. For the internal length, a value in the order of the material's average grain size has been found. Using the grain size isn't a general recommendation according to the previously concluded role of the internal length as fitting parameter, but maybe it's a hint for appropriate starting values for calibration. The calibrated model yields acceptable failure predictions of tensile tests with different notches and small punch tests. From these results, we cautiously assume that the validity of the considered GTN model reaches its limits if stress triaxialities smaller or equal to 1/3 dominate in the damage and fracture process zone. Thank you for your attention. An accompanying paper is available where the topic is discussed in more detail. The authors thank the German Research Foundation for funding of the research activities which have been conducted within the Collaborative Research Center 799 subproject C5.